Hi everyone, my name is Kaizen and today I'm going to be going through 2004 Step 1 Question 4. So this question was surprisingly quite easy, especially for Step 1. I think most A-level students would be able to solve this question, so let's just dive straight into it. So first we're asked to differentiate sec t with respect to t. So the derivative of sec t with respect to t. Now, this is a known result, but we're going to have to prove it. So the derivative of sec t with respect to t is going to be the same as the derivative of 1 over cosine t with respect to t. And here we can just use the quotient rule, right? So this is going to be 0 multiplied by cos t, since the derivative of 1 is 0, and then you keep cosine t minus the derivative of cosine t, which is minus sine t over cos squared t. So this is going to give us sine t over cosine squared t. We can simplify this to be sine t over cosine t multiplied by 1 over cosine t. So this gives us tan t sec t. Okay, so derivative of sec t with respect to t is tan t sec t. Now we're going to use that to solve our integrals. So it says, use the substitution x equals sec t to show that result here. So that's exactly what we're going to do. So we have I equals the integral from the square root of 2 to 2 of 1 over x to the 3 square root x minus 1, x squared minus 1 dx. So let's think about our bounds. So x equals sec t is our substitution. So we know that dx is equal to sec t tan t dt. And we know that when x equals 2, we have cosine t equals 1/2. Okay? Which implies that t equals the inverse cosine of 1/2, which is pi over 3. If you didn't quite get how I got this cos t equals 1/2, that's because, remember, sec t equals 2, 1 over cos t equals 2. That's what this implies. And then that implies cos t equals 1/2. Okay, I'm going to do the same thing for when x equals the square root of 2. That implies cos t is equal to 1 over the square root of 2, which implies that t equals cos inverse of 1 over root 2, which is pi over 4. Okay, so now we can write our integral as the integral from pi over 4 to pi over 3 of 1, but remember, our dx is sec t tan t, so I'm just going to write that at the top here, sec t tan t over x cubed, which is sec to the 3 cubed. Sec to the 3, sec t to the 3, multiplied by the square root of sec squared t minus 1 dt. So this is going to give us the integral from pi over 4, pi over 3. What do you notice cancels out? Well, one of those sec t's and one of the sec t on the denominator. So we're going to have here, that's going to be tan t over sec apologies guys, sec squared t multiplied by the square root of, now remember, tan squared t plus 1 is congruent to sec squared t for all values of t. So this expression here is simply tan squared t dt. And hopefully you can see more cancellations will start to arise. So this is going to give us tan t over sec squared t tan t dt. Tan t's go. Then we have 1 over sec squared t dt, which is equal to integral from pi over 4 to pi over 3 of cos squared t dt. Now remember, cos squared t, that can be written as 1/2 of 1 plus cos 2t. Okay? And that's derived from the double angle formulae. So we're going to have 1/2 plus cos 2t over 2 dt. If I just distribute that 1/2 there. Okay. So this is going to give us, now if we integrate 1/2, we're going to have t over 2 plus, not differentiate, integrate, sorry. I hope I said integrate. Now if we integrate cos 2t over 2, we're going to have sine 2t, not over 2, but over 4, because we already have that 2 there, the denominator. Now we substitute in our limits. This is going to give us pi over 6 plus sine 2 pi over 3 over 4 minus pi over 8 plus sine pi over 2 all over 4. So this is going to give us, when you simplify, pi over 8 is going to be plus 1 over 4. Okay, which is simply pi over 6 minus pi over 8 plus root 3 minus 2 over 8, which equals root 3 minus 2 all over 8 plus pi over 24 as required. Okay, perfect. Now, moving on to our second integral. Okay, again. Now, I'm looking at this integral here, and I'm trying to look for patterns. I'm trying to find how the integral in part I relates to the, part II relates to the integral in part I. Okay, so this is going to be, apologies. Now, it's always a good idea when you see these kind of integrals with square roots to complete the square and see what happens. So let's expand this out. What we're going to have, x squared plus 4x plus 3. Hopefully you can see that when we complete the square, we're going to have x plus 2 squared minus 4 plus 3 dx to give us 1 over x plus 2 squared minus 1 dx. Now that looks quite similar to the integral we had in part I. So why not make the same substitution? Okay. So if I make u equal x plus 2, that means du equals dx. Okay. I'm going to have the integral from 1 over u square root u squared minus 1 du Now, we're going to make the same substitution that u is equal to sec theta this time, which again means that du is equal to sec theta tan theta d theta. So our integral becomes sec theta tan theta over sec theta sec squared theta minus 1 d theta. Okay, those sec squares cancel. Oh, but looky here, I'm going to have tan theta over tan theta d theta because of what we said all the way up. Where is it? Up here. Okay. So this is just going to become the integral of 1 essentially. And that is pretty easy. That's just going to be theta plus our constant of integration. But what is theta? Well, theta is sec inverse of u. But what is u? U is x plus 2. And that is our answer for part II. Now, let's move on to the next. Here we have the integral of 1 over x plus 2 multiplied by the square root of x squared plus 4x minus 5 dx. Now, we're going to notice the similarity with the part before. It's part III, sorry. Let's complete the square again. So we're going to have 1 over x plus 2 multiplied by the square root of x plus 2 squared minus 4 minus 5. That's going to give us the integral of x plus 2 squared minus 9 dx. Now, pause here for a second. What was the idea? Okay, why did the previous two integrals work? Well, it's because what happened in here was that we were able to get, what were we able to get? A tan theta, because we could make use of this identity here, that tan squared t plus 1 is congruent to sec squared t. So let's see how we can relate that to this here. Now, notice that in all of these cases, we've had a difference of 2 squares. Because remember, 1 is squared. 1 squared here. 1 is 1 squared. And all the way back up here. Yes, again, 1 is 1 squared. So what's 9? Well, 9 is simply just 3 squared. Interesting. So that means that if we make the substitution that x plus 2 is equal to 3 sec theta, to then get dx is equal to 3 sec theta tan theta d theta, we will be able to manipulate this inside here to factor out a 3 squared. And then we can square root that and manipulate the integral to a simpler form. So let's get straight into it. So we're going to have the integral. We're going to have sec theta tan theta. Don't forget our 3 here, all over. We're going to have, now what was our x plus 2? 3 sec theta. So we're going to have 3 sec theta multiplied by the square root of, now our x plus 2 squared is going to be 9 sec squared theta minus 9 dx. Now, lots of cancellations can happen. That can go. So we're going to have the integral of tan theta. And remember, the whole idea was that we'd factorize out this 9 to get sec squared theta minus 1. Oh, apologies. This should be d theta. and this should be dx. Yeah, that was right. But this should be d theta. D theta. Apologies there. Okay, so we have tan theta over... Now, this is going to be... remember, the square root of 9, well, that's just 3. So we're going to have 3 here. And the square root of sec squared theta minus 1, well, that's just tan theta. So we're going to have tan theta d theta. This gives us a third integral of d theta, which is just a third theta plus c. Now, what was theta? Theta, well, if we divide by 3 on both sides, we're going to have x plus 2 over 3 equals sec theta. Now, that implies that theta equals sec inverse or arc sec of x plus 2 all over 3. Hence, our final answer is 1/3 sec inverse x plus 2 all over 3 plus c. Okay, a really nice question. I think this was very, very easy, even for step 1. So hopefully you guys found this very useful. Have a nice day, and I'll see you in the next video.